of data augmentation. One is to literally go out in the field and get more data. But if you can't get data, somehow generate more data. Let's say that you have an image. You have an image of a person, let's say this is a person with his hands raised. So what you can do is you can create one more data point by having him this guy stand on his head. Or you could do the data augmentation just by, so this is a rotation, right? You can do various rotations. You can flip left to right, right? So you could do, for example, a right to left, left, flip, and so on and so forth by various rotations and flips. The thing is, you're training. So suppose this is a cat. You can get a lot more images of cat simply by doing these things. The other thing you could do is you could just look at little patches of the cat. Right? This patch, this patch, this region, this region. And so by looking at subregions of an image, you can get more images. Now, once you know that these deep learning models, a lot of their lack of accuracy actually, there's a lot of overfitting always built into deep learning. Right? So you're dampening. The more data you give, the more you dampen it down. Now, why does it do that? The explanation for this is quite simple actually. Suppose you have 3 points, right? Or 5 points. So what will happen is you could do pretty complicated model like this with just 5 points. But now suppose I bring lots of, what has it done? This curve has gone and fitted to every point of the data that you see here. But suppose I increase the number of data points, let me mark more data points with a different color. Now suddenly you give more data points. More data points are, let me say here. Now what happens, guys? You realize that this thing cannot overfit. This white line or a flexible model, it will be forced to follow this path, right? It will be forced to follow the, actually let me use some other color. It will be forced to follow the path of the data, right? So it will be forced to follow this path. Would you agree that green becomes the best fit line now?
Yes, definitely.
So if that is really what the truth was, then you have reduced overfitting simply by getting more data. You have removed or you have regularized with more data. So that is the value of data augmentation strategies, or as simple as that, just going back to the source and saying, I really need more data. Right? With deep neural networks, no amount of data is usually enough data because some of these models are so ginormous that anything that you think of as a reasonable data can always be improved upon with more data. So that's data augmentation. Any questions, guys, before we continue?
So Asif, in this, when we talk about data augmentation, there's an implicit assumption that the sampling strategy was robust.
Oh yes, that is very, very important. So it is well shuffled and the whole thing is truly randomized. So the way we say that is, if the data is autocorrelated or somehow there's some pattern in the way, these things are not independent of each other, these data instances that you're learning from, then you are in trouble, unless you explicitly want to do that. So for example, if you're doing forecasting in time series, by definition, the data will be autocorrelated. In other words, the temperature tomorrow is highly dependent on the temperature today and yesterday and day before. Right? They're good predictors of temperature tomorrow. Right? So average temperature of this month, the moving average would be a good predictor of tomorrow's temperature. Other than those situations where you explicitly want that, in Everywhere else, you don't want that. You want the data to be truly independent. So what you do, what you say is this. Since you brought that topic up, I will throw in, I suppose, and if you guys don't get it, it's all right, but I'll just do that because it's not really relevant to what we do. People often use this word IID. In this literature, you will often find this word or this sort of, not word, what do we call this? This keyword or this acronym, IID. What does it mean? It stands for quite a mouthful. Uh, Independent and identically distributed. So what it means is that if you look at the red points, if that is the truth, the ground truth, that is the distribution. So all the data points that you're learning from should truly have come from the ground truth. You cannot mix two different ground truths and take some data points from one and take data points from another, because then no learning is possible. You're trying to, half the data points will try to take you towards function X, one function, another will try to take you to another function G, let's say F or G, and that won't do. Common sense says that if you want to model a ground truth, it better, all the samples must come from the ground truth, data generated by the ground truth, right? So that is the identically distributed part, right? The word distributed comes from the distribution, like how the data is distributed, right? And there's a bit more probability, etc. We won't get into, but later. Independent means this sample of data does not depend on the other sample of data that you picked. In other words, don't pick it in a sequence. Don't just go here, here, here. One by one, start picking the data. And quite often, so long as you're careful, and all you do is shuffle the data before training, you should be fine. So you must have noticed that in the data loader, if you go back and look at the code, data loader, you will see the syntax. You give the data set, you give the batch size. Do you remember? Do you remember, guys? You give the batch size. And what else do you give? You will see that I've given a parameter, shuffle is equal to true. Means for every epoch, every time it cycles through the data, in other words, in every epoch, you shuffle the data all over again. It's generally a good practice to remember and do this. Shuffle is equal to true. Are we together, guys?
Asif, one question. So the analogy of this image, rotation and shift left to right, is that exactly what, so we're talking about the augmentation of the data, meaning?
That is data augmentation, yes.
Yeah, original data is just one image and then you're creating augmentation by rotating it.
Yes, yes, that literally.
Okay. So that in doing that, you're actually increasing the more data points as well, right?
Yes, the number, from one you got to 3 data points, or 5 data points, or 10 data points. And you do that a lot. Generally, it's a good idea. And what you do is, I mean, if you're not doing data augmentation, you should ask yourself, why not? It's a freebie, right? Usually data is hard to get. But once you get the data, you want to squeeze the maximum juice out of it. So it is worth asking, why am I not doing data augmentation? You should always try to do that. Go ahead.
Can you do data augmentation with tabular data, or is this just strictly for imaging? And
you can
audio?
do that with interpolation, right? What you can do, and it's a little bit, I mean, obviously all of these things are fraught with a bit of danger. You look at the feature space, and if you can sort of get an idea, or see, again, this is a circular argument. If you knew the hypersurface that the data is close to, then in a way, that is what you're trying to learn. Right? But to the extent that you can find a relationship between some of their variables, some of the features, and you can reasonably interpolate between them. Yes, you can do that. See, one easy data augmentation for tabular data is they always come with nans, some gaps or missing values in the middle of your rows. Some columns of some rows will be missing, right? Column values. So when you go and put a reasonable value there, it is data imputation, what you call. You impute a value to that cell when it was missing. You are doing data augmentation, isn't it? You're salvaging an entire row of data that would otherwise have been, dropped.
Sir, what's about one-hot encoding a sparse matrix?
Oh, no. That is not data. That is just changing the representation of data. It's not data augmentation.
Okay, sir.
Asif, does that mean that whatever we use, smart to fix, to fix that data imbalance? So is that a data augmentation as well?
Yes, when you use SMOT, what are we doing? We are actually doing exactly what this interpolation business. We are interpolating and adding points. And so, as you know, with SMOT, the strength is that when it works, it's great. The interpolation is successful. The weakness is, if you are not careful, the SMOT will completely misguide you, right? And it will actually defect your performance.
Yeah, that's it.
We saw that, if you remember, in the boot camp, we saw that.
Yeah, yes, sir. Because this terminology is something new, so I just wanted to relate that with smart, handling the data imbalance. I just wanted to check with you on that.
Sure. Very nice. All right. So are we done with data augmentation? Now, one way that you could do the next strategy is called batch normalization. This is quite interesting. Every once in a while, we think we understand what it does, and then we shake our head and think, no, not quite. We don't quite understand what it does, because the way it works seems to be not the way we thought it works, right? Or why it works, rather. We know what we do, but we don't know truly, actually, very clearly, in uncontroversial manner, what it does. You talk to different people and they'll give you different answers. So I'm putting that caveat out because when you read at least these two textbooks these lab books and things that we have mentioned, they all seem to say some things which now we know may or may not be true. Right? Or that kind of wisdom is dubious these days. So what happens is that batch normalization comes partly to cure a set of problems. So what happens is that your data can get very big or small. It keeps shifting. Suppose you have one layer of data and you send a batch of data here, a batch. Right? What happens is that if all the inputs, now this data, the output of this is the input to the next layer, which is the input to the next layer. Now, what happens is that one thing that we know, or the reason you cook it up, is that you don't want these values to progressively, let's say, keep exploding or becoming bigger and bigger, right? Generally, neural networks don't perform well when the values are significantly shifted away from zero. You want your values to be somewhere within a narrow band of zero, right? Close to it, ideally -1 to 1 or 0 to 1 or something like that. You do want it to be there. But the output of your neural nets, obviously it's a response function. It is a sigmoid. Y hat is a some activation function. Actually, let me, by the way, I'll use sigma here because I'm in the habit of using it. But remember, it's activation function, any activation function. It could be ReLU. By the way, next time I'll talk about the activation functions, right? So it could be logit or sigmoid. These days people call it sigmoid. In the deep neural network, which again is a abuse of terminology, sigmoid. It could be tanh. It could be ReLU, leaky ReLU. What these words mean will gradually come to, but some activation function doesn't matter. So it is the activation of the Z, where Z is a bias plus weight dot x, the input of x. So a y indirectly is a function through the activation of this. Remember the box that we talked about, the magic box. Inputs come in, these are the weights, 1, W2. So here you get z by, z is a bias term, b plus W1 x1 plus W2 x2, which we succinctly write as b as W dot x. Right? And then you have this distortion function, the activation function that distorts it in some way. So now, when you do that, you don't know how big the values come out. And then you don't want those big values to propagate through. So what you do is, at each step, you take the output and you normalize it. Normalize as in, so what you do is, given a batch, a mini batch, you will compute the mu of the batch and this, well, I suppose sigma, because I've used sigma for standard deviation. Let me just use standard deviation of the B. You find that, and then you normalize every value, every value that goes into the next layer as, suppose you have a value, it's called the Z valuing. You take this, let's say that the input, well, Z is used for something here. Let me just use X prime. Any input that goes to the next layer, you subtract it and you divide it by the standard deviation. Are we together? So what you do is you subtract the mean and you divide it by standard deviation. So when you do that, typically values will be between -3 and 3, most of it. And in fact, most of the values will be between -1 and 1, right? So data becomes, the sizes again reduce. So that is batch normalization. Right? So one of the effects of batch normalization, so guys, any questions on batch normalization and why it is a good idea to do it? At this moment, take it as a fact that neural networks or these layers don't like it if the values are too large, inputs are too large.
So the normalization, it's happening for the given batch only. So the mu and the standard deviation is for that one batch. For that batch,
yes. So
is this to make the computations more efficient, or is it is this really to determine the behavior itself?
Yeah, so what happens is if you don't do batch normalization, by the way, was discovered in 2015. Very recently, we discovered that it improves the neural net. What happens is, if you bring in if you don't bring in batch normalization, especially for, let's imagine an activation function like this. And suppose the values all become very big. So you are in this region of the, irrespective of the weight, you end up in this region of the activation function, isn't it? Your Z will become large because your input values going in are large. Now, look at this. What is the gradient here? What is the gradient? Slope is?
0.
0. So what happens is learning is very slow. Right? It is very small. It's not quite 0, but you're creeping along in your learning process. Whereas if you are in this region close to 0, so here's the 0 value of a tan h or a sigmoid function, and then what happens? You have a substantial slope. This is where the slope is maximum. So anywhere close to 0, you'll have a pretty robust amount of learning at each step, isn't it? Because the slope is good.
But if it is at 0, doesn't that mean it doesn't need to be learned further? So it should stay at.
No. This is the input. If the input is 0, doesn't mean that the weights are 0.
No, I understand. But so this is the sigmoid function, output of the sigmoid function, right?
Right.
So if the slope is 0, doesn't that mean that the output is very close to the real number, the correct number?
No, actually it doesn't, because what happens is that, first of all, it will never be absolutely 0.
Not learning.
You are just far off. You're creeping your way back towards the right, picking up momentum and learning very, very slowly, right? Just because you saturate the activation function doesn't mean that you have reached the optimal point, right? You just have you have a situation of vanishing gradients. Your derivatives are close to zero. Yes, sir. Did you get that?
Yeah.
From a vanishing gradient doesn't necessarily mean that the loss function has reached a minima. It just means that you're trapped. It's just improving too slowly. You do batch normalization, it takes you out of that situation. You're moving along fine. So then the question comes, actually, that what has this to do with regularization? So initially people thought that you actually do regularize with batch normalization. Now, and there is some effect, but then it turns out actually that, well, maybe not, not quite. Right, and the situation has become tricky. Today we know that if you do batch normalization without bringing in residual short circuits, it's a concept that we'll learn about later, we are basically asking for trouble. Right? But that's a topic for later. But for now, in a very general sense, I think that batch regularization does have, normalization does have some regularizing effect. Oh, by the way, the one more regularizer that I should mention, let me mention is 7. That is sort of not a real technique, but it is batch size. Small. If you take smaller batch size, what happens is that you have a lot of perturbations of the loss surface. In other words, because you're learning from only a small amount of data, right? It is taking you all around, you know. You're just moving around, zigzagging around much more, fluctuating a lot more than with huge batch sizes. So another way to look at it is, see, if you have, imagine that this is your loss surface at this moment with this batch, B1. Then B2 comes and it draws a slightly different loss function. Then B3 comes and it draws a different loss function. So do you notice that the loss functions are fluctuating? Isn't it? So then what happens is, if you take smaller, the fluctuations are less if you take large batches, but they are quite high if you take small batches. That is actually a good thing, because what happens, imagine that you have a local minima. So let me take this white line. Let me take this white line and then going this. Now what may happen is this yellow line doesn't achieve a minima here, right? So one batch of data might have trapped you here, but the other batch of data actually happily sails you forward from that point and says, don't stop here, let's move forward. Do you see that, guys? Right? So suppose in the learning process, you are here. If this entire thing was your complete data set, you could get stopped at a local minima. But now, suppose you're fluctuating because each batch is a different set of data with different degrees of errors in it. So each of these batches of data will draw a different loss function. Will compute the loss differently with respect to the parameters. And so let's say that the next batch is yellow and it draws the loss surface like this. What will the yellow point do? So suppose you're sitting at this value. The yellow point will say, no, 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 you don't stop here. You continue moving downwards. Are we together? So having a reasonably small batch size is a good thing, which is why in neural networks, so if you never take the entire data set as one batch, you don't do what is called batch learning, batch gradient descent. Two reasons. The usual reason that is quoted is that the data won't fit into the memory, especially of the GPU, right? That's a practical reason. A more sort of a mathematical reason is you're much more likely to get trapped in a local minima if you use batch gradient descent. Whereas if you use mini batch gradient descent or stochastic gradient descent, which is a sort of a limit form where batch size is 1, you're much less likely to, because your loss surface is going through perturbations of it. Are we together, guys? Am I making sense? Guys, am I making sense?
Yes.
So I don't completely get it. So you're saying
Could use a picture.
So you're saying the smaller the batch size, the worse it is because we can.
No, no, no. I'm saying it's a good thing. The small
Okay,
batch
good.
sizes lead to the loss surface fluctuating. So if the loss surface is fluctuating, let us say that one batch told you that you have achieved a minima, right? The next batch comes and it draws the yellow line. So what is the next batch telling you? You
That was
haven't
not the
achieved the minima. There's more to learn. And so it just pops you out of the local minima,
right.
isn't it?
Yeah.
So it is a good thing.
Asif, one thing I didn't understand is how did batch normalization help us, come out of the vanishing gradients?
Okay. See, what happens is that, okay, let me explain that in simple terms. See, suppose, and this is best explained with a tan H or a sigmoid activation function. It's a very simple idea. See, look at the sigmoid activation function. It looks like this, right? So this is your yx is equal to minus x. Or in our term, let me just use the word z, right? Because it is z. So now what is z? Z is bias plus, for a given node, it is bias plus W1, X1 plus W2, X2, etc., etc., right? Let me stay with two nodes for the time being. Right? So you have a node here, 1, 2. So here, the output of this is, let's say, X1. The output of this is X2. And they feed into, let's say that this particular node here. And there are many nodes, but let's look at this one. So now Z here is what? It is the weight W1, W2, right? Now see what happens. If any one of these values are large, then Z will be large.
Yeah.
Now look at this axis. This is your Z axis. Because this activation is working on Z. This is your Y of Z. So what happens if Z is here? Look at this. What is the gradient here? What is the slope here?
Zeros.
Approximately 0. It's infinitesimal. So the learning is just creeping along, right? It is not quite 0. So you learn a little bit every step, but you pretty much are, the entire thing is just creeping along. Whereas if your X1 and X2 are small, now the weights are, let's assume that the weights are small. Then what happens? If your value is somewhere here, some small value here, at this point, what can you tell about the slope?
It's a finite slope.
Yeah, exactly. So these are pretty healthy slopes, right? These are not vanishing slopes.
So, sir, neural net is not good for sparse data set.
No, so that's a different discussion. Yeah, why do you say that? Why do you bring that up here?
Because if the data points are way too far, then it's just will not learn properly, right?
Yes, sparse data and neural networks don't quite go together. That's a point we made a little while ago. You can regularize it, except when you're using transfer learning. See, transfer learning, when you use it, it's a form of Bayesian learning. You start with a very strong prior.
Yes, sir.
See, when you take ImageNet data, ImageNet, a model that has been trained on ImageNet, let's say, as we did, right? It has been trained on pictures in ImageNet, and let us say that you tweak and you train just the last mile. What are you really doing? You are starting with a prior, saying that this complex deep neural network, I know I'm very close to the right answer. In the parameter space of weights and biases, this is where we should be, somewhere around this region. And we are going to tweak only some last layer, weights and balances. Right? If you really think about it, transfer learning is saying that we are starting with a very good prior, very informative prior, and we are just doing a Bayesian a posteriori model that comes out of just the last layer. our last couple of layers. So if you do that, then small data sets are enough. In fact, that is why I started this workshop with transfer learning. Like, look at your data problem, ask yourself, is it similar to a problem that has been solved? Is it, within reaching distance of a problem that has been solved? If you can map it to a solved problem and you say, well, this is an adaptation of that, then what can you do? You can take the model that already is there and you can essentially treat it as your Bayesian prior. All you're doing is tweaking it. So then even a small amount of data will work for you.
But we call it say data greedy algorithm, sir. So even with a small data set, in the end, will produce good results. Isn't it data?
See, here's the thing. When you use that transfer learning or fine-tuning a pre-trained model, you don't need much data. But then to pre-train it in the first place, you needed a lot of data.
Yes, sir.
At some point, a lot of data was fed into the neural network and a lot of training took place to really find the minima in the parameter space where the loss minimizes. With that, now you're doing transfer learning. So that's a world today. If you train a neural network from scratch, you better have a lot of data. But the one trick is, if you do have pre-trained models for a similar problem, not quite your problem, but a similar problem, then you can transfer the learned model. And even with small data, you're just doing a last mile training.
Yeah. So, sir, small question here. So, in the last layer, we are teaching, let's say we have only two target variables, or you said, let's say just cow and duck.
Yes.
Why do we take the prior? We just train on cow and duck and just start from there.
That is, so let's take the example of cows and ducks. A cow and duck, you can't classify as images. Those are images. There's a lot of information in there. So you need a pretty deep neural network to train it. So the
Yes.
question is, do you go and get 1,000,000 cow images and 1,000,000 duck images and train a neural network from scratch? Or do you take a neural network that has been trained, pre-trained on all sorts of animals, but maybe not on cows and ducks, but it has recognized, it knows how to recognize a truck, a house, a tree, and so on and so forth. So it has learned to understand geometries of objects, right? And therefore classify them. Do you want to take, it's called representation learning, and that's one of the topics in the coming weeks. It has learned a lot. It just doesn't know cows and ducks. You want to take that model because then you don't need a lot of pictures of cows and ducks. You just need to do a last mile training. Last layer training. So the last couple of layer trainings at the head.
So yeah, if the prior model doesn't have no information for cow and duck, sir, so what is the usefulness of that? That's my thing.
You might have recognized horses and zebras, right? And monkeys and whatnot. And that knowledge is not that far. Ability to recognize a monkey, a zebra, right? A zebra, for example, is not that far from a cow.
Yeah.
Yeah, that is the point.
Now I understand, sir. It's that problem is hot dog and not a hot dog.
Right.
Now I understand. Sorry. Yeah. Got it. Thank you.
All right, guys. So now, Nisarg, it answers your question about this, right?
Yeah.
So batch normalization, one of the things we ask is to what extent it regularizes or doesn't regularize. There are a lot of schools of thought, actually. Some people, I mean, if you read the classic, everybody will say, yeah, it's a regularization technique. But actually, some people argue, no, it is actually causing instability. Unless you introduce residuals, it won't actually work for you and so forth. So, so there's a little bit of thinking going on. But bottom line is, should you batch normalize? You should always batch normalize. It's a good idea. But whether you do it for regularization or not is a different question. Probably not regularization. You do batch normalization because it's a necessary thing to do. You must do it.
Hello, sir.
Yeah, 1 second. So guys, remember that when I always tell you that in ML 100 and 200, I've said, whenever you do machine learning, learn on standardized data, scaled data, isn't it? It is the same thing extended forward. See, each layer, suppose this is layer 1, layer 2. What is the input to layer 2? It is the output of layer 1. Right? If you think of layer 2 as its own model, then you would agree that it is a good idea to feed it normalized data. Just as input we normalize, we should normalize the input of each of the layers. To do that is batch normalization. Yeah, go ahead with the question, please.
So in this case, right, when you do the batch normalization and compare it with the normal feed forward network,
yes,
the node in your hidden layer, every node then need to have an activation function.
Every node always has an activation function. No?
I mean, when you talked in your previous session about the feed forward network,
right.
the output node had an activation function, not all the nodes in the hidden.
So I think, so let me clarify that. See, every node, when the definition of a node, def of a node is always this. You compute Z and then you distort Z. You do some distortion function.
Okay.
Right? You always apply some activation. So in other words, the output y hat of every node is the activation of Z, where Z is the omega naught or bias or whatever you want to call it, the W1, X1, WN, XN. Huh?
Okay, thanks for clarifying.
Yeah. This is a gift.
As if we introduce, for batch normalization, if we introduce a large set of data again, will this affect the batch normalization because your standard deviations would shift and your possibly your mu also?
No. So your question is, if you increase the batch size to quite an extent.
No. As if we introduce extra data.
Oh.
Like a large set of data.
All right. See, the law of large numbers is there. What it means is that whenever you take the data forward, right, if the data has been sufficiently randomized, then you don't have that problem. Remember, you're using it to train the weights, right? During the training process, you're passing mini batch after mini batch. What happens at the end of it when all your weights are fully trained? Right? You freeze all the weights and everything, and you just make predictions, one data point at a time or one batch of data at a time. That's that. All right, so that's for batch normalization. Let's move forward. We'll come back to it again. This thing, right? Today I introduced the concept. We will be coming back to it again and again. The next thing is early stop. So what happens is that if you look at data, if you look at the training process with early stop, it is the wisdom is that after a little while, say, it is like this. The training loss by, let's say, the number of steps keeps on going down, right? But, so in other words, this is the training loss. You keep on training and it keeps going down. And you observe that the test loss tends to go like this. Oh, this looks somewhat like your bias variance trade-off, right? This is exactly that. You realize that this gap is your gap of overfitting. You don't want the training, the model to learn from the noise because it's so flexible. First, it learns from the information, and gradually it has no more to learn from the information. No further information left. So it starts eating up the noise and starts fitting to the noise. So one of the strategies that you can use is you could have an early stop. And what you can do is you can literally, so the way people do is early stop is you can just take a few epochs and freeze the model, save the model. And if you want to run more epochs, you load the model back from a, let's say, persisted file, and then continue and run a few more epochs, and you do that. The advantage of early stop is, well, of course, you don't overfit. That's a form of regularization, preventing overfitting. The only problem is, when do you stop? Right? And in a way, it mixes two separate things, which is why some people frowned on it. See, what it does is, when you are training the model, you should find out which features matter and what should be your neural architecture, and so on and so forth, right? You should be busy with those considerations. And later on, you should worry about early stop in a second phase or something like that. Like you regularize, you do this, performance, you improve the accuracy, etc., etc. With early stop, what happens is you sort of doing everything in one go. So people say that you break a concept called orthogonal concerns. First, you train a good model, build a good model, and next you worry about when to stop or how many epochs to run it for. These are two separate concerns. So that is as it is, but early stop is a valid way of doing it. So how would you do that? Suppose you run it to 1 epoch, 2 epoch, 3 epoch, 4 epoch. You have to judiciously stop. So suppose here, you suspect that the inflection point was here. At this moment, you can just save the model or stop the model, save the model. Then see what sort of accuracy you get. Then go try it on test data. You say, oh, test data, train it. Now here you do again, and after a little while, you do one more epoch, and you realize that you should have stopped here. Whatever model you saved here was your best model. Right? Model and the epoch I was your best model. You don't want to go to this, and it's time to abort the moment you see the gap increasing again. Are we together, guys, now on this? So early stop is simply just saying that I will run the machine for 100 epochs, but not really. The moment I see the gap at each epoch, I'm looking at the gap between test and training loss. And the moment those losses begin to diverge from each other, I stop.
What was that term if violating the purity or principle of sticking to like the training data? You said it was the orthogonal something?
Principle of orthogonal concerns. See, this is a basic architectural thing.
Oh, okay.
When you're doing something, do just that. Don't do two things at once. Do one thing, then go do another thing. That sort of thinking.
I have a question on the. Is there a way we can just use the elbow method on the training data itself to figure out early stop?
No. So look at this. The white line is the training data, and the loss keeps on decreasing. There is no
But what
elbow.
if at the optimal point there is an elbow instead?
No, there isn't actually. Sort of. I mean, you could say that you reach an elbow, but the point is that you don't know whether that elbow has already overfit. You don't know that. So suppose your training loss falls like this, and you stop here. How do you know that this is where you should have stopped? You have not already overfit.
Yeah.
You don't. So you just have to use. I mean, see, quite often this will work, but you're not 100% sure. Go back to the lab, guys. When I say all of these things, it is all in the labs. Now, when you go back and review the labs, do you notice that the last lab, when we tried to fit a regression model, it looked like this? Does it look like this, guys? With a lot of wobbles? You can see some of it there. And anyway, we'll do a lot of labs after this, and you'll see the effect of all this. So this is early stop. Let's go back to our method. So we did ensemble, we did data augmentation, batch normalization, early stop. Now comes an interesting idea called dropout. I'll do the dropout, and then we'll take a break, and then we'll come to L1 and L2 after that. So guys, are we together so far? There's a rich variety of regularization techniques. And so we are learning a lot. I would strongly suggest after this, read the textbook. The textbook has a chapter. It discusses regularization and gradient descent very well. So one thing, reading material from the textbook is read chapter 4 which is gradient descent. Well, it is numerical computations, but it talks about gradient descent quite a bit. Numerical computations. This I mean from which textbook? The main textbook, not the lab textbooks, the deep learning textbook. The first textbook on our course webpage, right? Chapter 4. And then I forget which chapter has it. One of you, if you have the book in front of you, just look it up and see where the chapter has regularization in it. But do read regularization from here to review the material.
7.
Chapter 7.
Yes.
So chapter 7, you can jump straight there and see, try to understand that. So now I will talk about, what was I going to talk about?
Sorry, one question on this graph, comparison between the test loss versus training loss. So is it always that the test loss there will be a point where it will start to go up and then it will keep going? It will not like after it will come down again, meet training loss.
Yeah, that is one saving grace, that once you start losing it, there is no test loss, there's no getting better after a while.
Okay, because our assumption is based on that fact that it is once it starts to separate out from the training loss, it's always going to go up.
Exactly, it does.
Okay, all right.
But that's a very good question that you asked. Nice. So guys, now we'll talk about dropout. What in the world is dropout? And what it means is, it is like playing the game of Cheshire Cat. Do you guys remember the story? I don't know if you know. There's a story for children, and it always reminds me of that. It is Alice in Wonderland. So the whole idea is that Alice goes down a rabbit hole, and she is in this magical and wondrous land. But one of the disconcerting things is that there is this cat that seems to suddenly appear and start grinning at Alice and saying something or the other, right? And Alice sort of finds it disconcerting that it suddenly materialized out of nowhere and then it disappeared, right? So there is something of that quality to this dropout business. What it says is that, suppose you have a layer which has, I will just take 8 nodes. 1, 2, 3, 4, 5, 6, 7, maybe 8. I'll just, because so that I can illustrate it, the point. And let us say that the neural net, the input data is flowing in to this layer. What you do is that for every once in a while, every step of the process, right? Whatever your step is, you just nuke some of the nodes. You, for example, will go and first of all, you take these nodes out of the picture. It's almost like these disappear. Now, how many nodes do you see? You see only 6 nodes. So the data flows onto 6 nodes. So what happens in reality is the nodes are there, but you just switch them off. You drop them from the learning. You just switch it off. So whatever weights they're holding on to, they'll hold on to. But they will not contribute. They will not contribute to the forward and the backward, the process of the whole thing, right? The learning process. And then the next time around, you'll go and nuke some other nodes, these two, and bring those 2 guys back. And then suddenly you'll nuke this and that. And so randomly, you will keep dropping, in some sense, nodes from the layer as different steps of the learning take place. So it has the same effect. What it does is that, as you can imagine, what essentially the loss surface, right? It causes little changes in the loss surface, right? And those perturbations are good because they prevent you from getting trapped in local minima. So this technique is called dropout. That is all the idea there is. So dropout is good, but remember that it introduces noise or fluctuations in the loss surface. Step to step, you see it fluctuating continuously, right? And that fluctuation is good. So imagine that you have a loss surface that continuously vibrates in some sense. If it vibrates, then if you are in a shallow minima, what will it do? It will, if you are a marble, it will just bounce out of that. Right? That is the purpose of it. It just keeps tilting a little bit, fluctuating the loss surface. So that method is called dropout.
So Asif, does this work similar to the wisdom of the crowds, where you, by inactivating some nodes, you create like a weaker learner?
Let me think. I know where you're coming from. I wouldn't map it to that. See, in, like for example, in random forest, right? Randomly you pick a subset of the in feature space, isn't it? There's a little bit of an analogy to that. See, when you build a tree in a random forest, what do? At each moment, you don't span the entire feature space. You look at a subspace and you take only those features to learn. Now, the output of all of these are like that. They are features. They are features or the inputs to the next layer. So by passivating or just shutting down a couple of those nodes, what are you doing? This layer, next layer, just sees a random subspace of the, so far as this layer is concerned, layer L of the L minus 1 of the L minus 1 output space. You realize that if you nuke 3 of these nodes, then essentially 3 dimensions are gone. You're looking at a random subspace, right? And those random subspaces, generally, what does it do? Remember, random forests get their regularization from exactly that. You remember that, Patrick, from our ML200, isn't it?
Yes, Asif.
Right? So you have a very similar effect here. By using dropouts, the next layer is getting not the whole data, it's sort of being forced to get only a subset of the data. A subspace of the data is looking into and learning from. So that's the value of it. So that's what a dropout does. And guys, we have been at it for about an hour. Do you guys want to continue and we finish the L1, L2, or would you like to take a 10-minute break?
Either way.
We can continue.
Let's finish.
Let's finish it, right? Okay. So then, as I apologize, today's session would be longer. By the way, we again have a choice at this moment. We can just summarize what we have learned. We learned quite a bit of that. And next time, take the L1 and L2 regularization. That is possibility number 1. I could cover the L1, L2 regularization on a Saturday extra session, and then Monday we move on with the new topic, or we just push it to, we either finish it right now, or the other is we just move it to next Monday. So any particular opinions or suggestions?
Let's finish it today.
Let's finish it. Excellent. So this one,
I see one question. Sorry.
yeah, go ahead.
One question on this dropout one. So you for a when do you bring them back? So let's say I dropped out 3 nodes.
The next step, you bring them back, and then you
It's
go, yeah, and you kill 2 other nodes.
So is it the next step or next epoch?
That's a good question, actually. It's the next step.
Next step, okay.
The next step itself, so the thing is that your error surface fluctuates quite a bit. And you get the same thing, or in my view, a very similar effect as you get in random forest.
Okay.
We are looking into subspaces now, random subspaces. And taking random subspaces has been a very effective way to regularize or diminish this. Many algorithms. So now let's come to L1, L2. The word L1, L2 from, so let me give you the root of it. See, first of all, a very quick one. Suppose I have 2 points. You are at, let's say that you are in a city. and the city is on a grid, right? So suppose you are at this point. Let me call this point X, right? And suppose you want to go to a point that is, let's say here, Y, right? This point. So what is the distance between? So the question is, what is the distance between X and Y? How would you answer that, these 2 points? Now, you may be tempted to say that the distance is very simple. I just cut across, and that's my distance. Are we together? Right? So you can say distance, an intuitive definition of distance would be as the, let me just write it as one definition of distance. Distance is the shortest path as the bird flies. You would agree that that's a pretty good common sense definition of distance? Anybody, guys?
Yeah.
Yeah. And how would you compute this distance?
Manhattan.
What happens is you would say y, so suppose x is made up of components. Actually, x1, x2, x1, x2, these are the x, and this is made up of y1, y2. You would agree that this distance would be square root of x1 minus y1 square plus x2 minus y2 square. You know, this is just the Pythagoras theorem. Namely, this part, this much is x1 minus y1, right? And this part is x2 minus y2, or the other way around, right? I should say y, actually, why don't I write it correctly? And use a different color just to emphasize this. So this distance is y1 minus x1, and this distance here is y2 minus x2. Would you agree, guys, that this is it, right? And so what does the Pythagoras theorem say? The hypotenuse, which is your notion of distance, is this, right? Hypotenuse square is the sum of side squares. So this is often called the Euclidean distance. So Euclidean distance is as the bird flies. But then if you are in a city and you are a Uber driver or a taxi driver, you would beg to differ. You say, well, you know, my petrol or the gas that I end up using and the time that I spend clearly disagrees with this definition, because the best that I can do is I can take this path from here to here. This is one path, or I could take I could take intermediate paths. I could take this path, go up, and then go here, or I could take, I don't know, different paths you can imagine, or I could just go up and go here, right? Any one of these paths, if I take, they are all of the same length, and the taxi driver's distance, what will be his distance? It would be the absolute value of the size of this distance and this distance, right? It will be y1 minus x1, the absolute value, you know, the actual size of the base plus actual size of the side, right? First you go east and then you go north, and whatever in absolute terms, whatever those things came to, that would be the distance. So that will be the taxi driver's distance. Would you agree, guys? Right?
Yes.
And the distance is very practical. You know, your odometer will say that, your gas cost will say that, everything will say that. Why? Because the taxi drivers are usually not allowed to rush through the buildings. Right? So this distance is because Manhattan was, I suppose, one of the first cities laid on a grid. This is called the Manhattan distance. Now, what has this to do with regularization? It turns out it's quite interesting. It has to do with one thing. And let's connect the dot to regularization. We will ask, what is a circle? What is a circle? So one definition of circle that you would agree is, let's say that you're sitting around, you're making a circle around origin. Yeah. It is the set of all points at unit. So what is a unit circle, just say, right? So unit distance from origin, right? So in other words, this is 0, 0. And then you can draw, for example, you find all the points that are at unit distance from the origin, right? So then something gets very, very interesting actually. What happens is that when you're looking at Euclidean, this is what you're familiar with, you are at this distance and you can fly anywhere the bird flies, and your circle looks like this. This is being 1 unit. Does this make sense, guys? So in Euclidean, with Euclidean distance, this is your unit circle. Are we together, guys? Any doubt? This is very, hopefully, a very obvious statement. So this doesn't look very remarkable, but if you take Manhattan distance and you say all points that are at unit distance, now the thing begins to get more interesting. So I'll just draw the grid here. Lots of it. So here's the thing. 4 units. So the taxi driver can go 1 unit here, or the taxi driver can go a 3/4 of a unit and 1/4 unit up, or the taxi driver can go half a unit and half a unit, or taxi driver can go 1/4 of a unit and 3/4 of a unit up, or the taxi driver can go 1 whole unit up, right? This is 1, this is 1. If you connect these points, what you get is this. And so by symmetry, you realize that you're looking at, and this, you just defined your circle to be the set of all points at unit distance from origin. So you say with Manhattan distance, your circle looks like a diamond, like, okay? So to make it very practical, suppose you have 1 gallon of gas. How far can you go? And suppose your car can give you exactly 20 miles a gallon, let us say. You would agree that this would be the set of all points, the outermost set of points that you can reach with your 1 gallon of gas if you're a taxi driver, isn't it? So this is it. So now it turns out that you say, well, that is very interesting. Your unit circle shape depends upon your definition of distance. So it turns out that the guy who first generalized this idea from Euclidean to this was a guy named, a wonderful mathematician named Minkowski. And so named after him is the concept of Minkowski norm. He says that the distance between 2 points, x and y, based on the norm, the n is the norm, is equal to, what you do is you take the gap between x1 minus y1. I'll just take 2 dimensions for the time being, to the power n plus x2 minus y2 to the power n, and you can generalize it to higher dimensions, this, and the entire thing to the 1nth power. So now let's see, does it work out to the Manhattan and the this thing. What happens when you take 2? When n is equal to 1, what does it become? It becomes, d1 becomes x1 minus y1 plus x2 minus y2. This is the same as your Manhattan, isn't it, guys? Now, on the other hand, when you take d is equal to 2, or n is equal to 2, the second notion of distance, this becomes x1 minus y1 square plus x2 minus y2 square, the entire thing square root, right? 1 over 2 power. Now you realize that when you take even powers, you don't need to take mod. You can just take the difference and square it. It will automatically be a positive quantity, d2. So that is it. Now, what has that to do with our loss function? Before I get there, we are very close to the final connecting all the dots. I want to make sure that we understand what the Minkowski norm is and the generalization of the notion of distance to an arbitrary norm. Are we together, guys?
Yeah.
We are together. So now let's connect the dots. And here I will state something without a proof, but I just state it because we don't have that much time, and also because for many of you, we have given entire sessions to this. Now let's bring up the idea of L1 and L2 regularization. Loss by foot. Sorry, guys. Sound, is it just me? So what we do here is quite interesting, actually. You say that your error function, remember we said that the error function, the loss function, the error function used to be like this, the error surface. Let's say some squared error, y minus y hat squared summed over I. And if you need, you can even average it. Mean sum squared error, that's what we did in lab 1. So what do? You look for the minima here, isn't it? Are we together? But suppose this is your XY axis. This is your absolute minima. This is the origin. Now I set a budget. I tell you that you cannot go more than a certain distance, right? I set a budget. You say you can go only this far. Now remember, what are the axes here, guys? This is your parameter space, right? This is the space of your, let's say that you have a parameter here, some weight, some parameter is like this, and this is the error function. Right? Why? Because this can be written as yi minus bias minus w dot x, let's say in single dimension. Right? Now xi and yi are constant, so this error function is actually a function of w. Right? I'm gobbling up the summation and so forth. Actually, why gobble it up? Let's write it down. So you realize that, see, when you're learning, the error function depends on the weight. What is the parameter value? And I'm just keeping b as constant for the time being. I want to show things in one dimension. So guys, are we together? This is the equation. The only thing you can play around is go to different points in the parameter space and see what the error value is, right? What the total error is. And you're searching for the best point. So typically, if you're minimizing, suppose you start here, you will ultimately gravitate to this. Make sense, guys? Guys, am I making sense?
Yes.
So you would gravitate up, 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 there. You would end up here. But suppose I put a constraint on you. I say, you know what? You can only search This is the permissible set of values. Permissible. Okay, allowed. Let's just use a simpler word. Allowed W's. Range of allowed W's. Allowed W values. So you can pick any value here, etc., etc. So then what would happen? Then something very interesting would happen. The lowest that you can achieve is this point, isn't it? This is, I will put W tilde here, and isn't it, right? Because the lowest loss that you get within the region that you can travel is at this point. At any other value, the error is more. Am I making sense?
Yes.
I say you cannot go too far from the origin. I've given you a budget. This is the limit of how, this is the distance that you can go from the origin. But then you have to find minima, whatever the lowest value is within this region. So now you're not looking for the absolute minimum of the error. You're just comparing this value with other values of the errors, right? Other values here. So your gradient descent will stop here. At this point, you'll run out of budget. Isn't it, guys? You've run out, if you're a taxi driver, you have quite literally run out of gas. So when you do that, and I'll state this without the mathematics, the proof, etc. behind it, what you say is you have actually regularized the problem. You have prevented overfitting. So what happens here is this point leads to overfitting. In complex models, the absolute minima is overfitting. Whereas when you constrained it, so this problem is called problem of constrained optimization. Constraint means you have constrained the search space to a finite amount from around the origin. Optimization. And there is quite a bit of theory about constraint optimization. And I would just explain that in the next few minutes, and you'll see it. It's very elegant. Now, everything that I'm going to say that I explained in one dimension, it can be generalized to higher, and I'll show it to you in 2 dimensions for a moment. But this is your best solution. This is your best solution. You stop here. And it turns out that if you stop here, you will have reduced overfitting to a large extent. Now, the whole question is, how in the world did that happen? And there's a very interesting clue to it. The reason it happens, again, I'll state it. Let's peel the onion a little bit and see what is going on. What happens is that when you have overfitting, your weights or parameters, it could be a biases, your parameters become large. When the parameters become large, it's a classic sign that you have overfit. Right? So at this point, if you look at it, you're too far from the origin. Right? But then you have overfit. On the other hand, so one easy way, so this is overfit. Now, why that happens, we'll sort of skip it over. So if you force the parameters to remain small within a budget, you therefore do constraint optimization, you regularize the problem. Now, let's look at it in 2 dimensions and what it looks like. See, when you look at this in 2 dimensions, suppose this is your B and W, you know, suppose you're writing Y is equal to Y hat is equal to B plus, right? Think of it, the 2 parameter space, and here is your error surface. What happens is that somewhere there will be a minima, right? And let me draw the contour lines here. 3 contour lines. What happens is that there will be some point, let me just call it W star, right? Which is made up of some combination of, let me just use the vector space. Some point, a parameter value, which is a combination of the best B and the best W, this point. around this point, if I project onto this plane, if I project these error surfaces, you will find that these lines are there, right? These are your contour lines. These you call contour lines. What are contour lines? Is the shadows on the plane of equal error surfaces. You agree that if this is the error axis, all the points on, let's say, this pink line, they all have the same error because they are the same height from the plane. So when you project it down, it will become this. So, well, not quite accurate, but okay, it will project down to this. Right? So these lines, which are contour lines, it comes from geology, right? But they always show maps or hills using contour lines. So we get contour lines for the error surface, right? And we can find the point of the absolute minima. But then comes something very interesting. If you constrain the budget, see what happens is we can keep drawing the constraint line like that. But if your budget is fixed, let me put the budget in another color, green. If your budget is fixed in some way, whether it's a, let me just take a circular budget here. I'm trying to draw the circle in that plane, in the BW plane. Let's say that this is your budget. And you have to find the minima here, somewhere in here. So what is the lowest point that you can find? Would you agree that the lowest point is here for the error, right? Let us draw it out in a piece of, in a two-dimensional plane, and this becomes obvious. What happens is that, suppose you have a circle, and you have this point, these contour lines are here, and as you go outer and outer, they represent greater error. So let me just say A, B, C, D. So the error of A is greater than error of B, is greater than error of C, is greater than error of D, is greater than the best error, which you have E. This is the smallest error. But any line that you take, let's say A, let me take this thing as Q. EQ is greater than this. So what is the best you can do, guys? In this space, within this circle, what is the point of lowest error? It is this point, isn't it? And this is the best solution that you want in the parameter space. Whatever the value of B here is, let me put a tilde here and a W here. These are your best values. Let's say that this is B and this is W. And this one, which is the absolute minima, B star, W star, you don't take that. That leads to wild oscillations. It leads to overfitting. You instead pick this solution. Now, there is a little bit of a elegant mathematics to that. I'll just mention it in the next few minutes. This is only for those who have taken courses with me or who like to be mathematically interested. See, what happens is that this is a constrained surface. What is this? This is a surface whose equation, so suppose you're looking at Euclidean, it is B square plus W square is equal to some constant, G. G as a function of circle can be written as D B W is equal to this, is equal to some constant, some value C is your budget, right? Or C square if you want to think. That C square is your budget, right? Radius is C. Now, the loss surface, the error surface is whatever it is. At this point, you would agree that these two lines are tangentially touching, right? So the perpendicular vector to these two, they will be pointing in opposite directions. Would you agree? The point at which the budget surface touches the error surface, just glancingly touches, then the perpendicular vectors to each of these two surfaces will be pointing opposite to each other. The direction in which they are growing. So how do you grow this constrained surface? By taking a bigger surface. How do you get more error? Go from inner to outer. So this would be, and there's a notation for this, this you call the gradient of error, and this direction is the gradient of G, the constrained surface. Right? So you say that gradient of error is actually a negative of the gradient of G, and what is gradient I'll come to in a moment, up to some proportionality factor, some lambda. You don't know. All you know is they are opposite to each other, but you don't know what the proportionality factor is. And you come to this beautiful result. And by the way, this reasoning was argued not just in machine learning. The first person, the mathematician who argued doing optimization with constraints was a guy named Lagrange, a mathematician, a famous mathematician named Lagrange. And this lambda is named in his honor. It is called the Lagrange multiplier. Lagrange multiplier. And if you remember way back when you did college engineering, you must have learned about multivariate constraint optimization and Lagrange multiplier, but I've essentially reproduced the theory here. Now let's see what it means. The error was y minus y hat square, the usual summations, and then if you want to put a 1 over n, you can put a 1 over n, which serves no purpose. I'll just skip it, assume that there's 1 over n. Now, if you look at this equation, it says grad of E is equal to minus lambda grad of G. By the way, this grad is generalization of a derivative. Derivative or slope, gradient, right? Gradient. And the reason we call gradient descent is actually because of this inverted triangle symbol, which is the gradient symbol, grad symbol, right? Del symbol. So now this equation can be written furthermore. From this thing, we conclude that we can write it as gradient of E plus lambda G is equal to 0. In other words, we can think that we are minimizing this. When the derivative vanishes, we have minimized this, right? Minimizing this. So the word that you use is, it is your loss function. Loss function, L, typically written with the calligraphic L, right, is equal to, which is a function of the parameters, let's say B and W here, is actually E plus lambda G, where this term is obviously some squared error, let's say for regression. And this is applicable to classification also. It doesn't matter what it is, but let me just write it as y minus y hat square plus lambda. Now, what was G? G is the equation of a circle. In the case of B square plus W square, so people often write B as W naught, right? So I'll just write it as W naught square, W1 square. And what happens if there are more terms, it's higher dimensions, it is W2, WK, whatever the dimensionality of the data is there. And so you're saying that it is error term, the initial error term, your E term, I'll just write it that, plus, or let me write it explicitly, y minus y hat square plus lambda summation over all the possible, some other index. So this is I, this is the data index, but this is a K, suppose it is P dimensional. So K, W, K square up to P. Suppose there are P dimensions, right? So that's that. Does it make sense, guys? Are we together?
Yes.
Right. And this is a bit of a mathematical thing. This is your loss surface. Now, we took a circle which was Euclidean. In the case of a Manhattan circle, remember your constraint surface is X, like the absolute value should be constant, Wi. Let me write it in the simpler term because we use B. The absolute value of B plus W should be some constant, right? Which means that if I write it in the new notation of W naught plus W1 plus W2, generalizing it, etc., to WK is some constant. And so your regression, this loss function therefore becomes loss function for L1 norm, that is when you take Manhattan distance is your standard error term. By the way, in the case of classification, it wouldn't be the sum squared error, but whatever it is, y hat squared summed over. And if you want to, by the way, divide by n, go ahead and divide by n, but I'll skip it because it doesn't affect you. Then times lambda. In the case of this, now this you can write it as sum over k, absolute value of k, right? Up to p terms. This is k up to p terms wk, right? So this was a mathematical digression. Again, if you are not up to the, if you haven't been with me for a while, you might find this a bit rushed. It doesn't quite matter. Just remember that L1 and L2 regularization, their main goal is to make sure, so let me point to it. So their main goal is to make sure that the terms don't blow up. The weights, the parameters don't blow up. Right? L1, L2 goal. Keep Wi, all the Wi small. Are we together? And when you do that, it achieves regularization. Are we together, guys?
Yes.
Yeah. And that is the famous L1, L2 regularization. Right? So I will review this L1, L2. Like if you are completely new to this, it may feel too much geometry and too much mathematics, but you can sort of short circuit and take a flight over all the mathematics and reach a final statement. The final statement is L1, L2. Their goal is to keep the weights small, and they manage to achieve it using some very interesting arguments, right? Mathematical arguments of why it works by fixing a budget. Right? And so they introduce their own hyperparameters into the model. How much is your budget? How big are you willing to see the size of W grow? To what extent can the weights and biases grow? You have to set the budget. That's a hyperparameter in the model. All right, guys. So we'll come back. Today we were a bit ambitious. I wanted to cover regularization, and I also wanted to cover gradient descent and show you guys, I mean, not gradient descent, backpropagation, and show you loss surface. I would like to still show you loss surface in the next 15 minutes, but let us summarize where we are. So we covered L1 and L2 also. Okay. We covered 6 or 7 methods, let's say, of regularizing, and come up with more of your own, if you can think of something. Contribute to the field. Right? So here we are. These are all methods to regularize a model. Regularization is to prevent overfitting. Right? It is to prevent a model from just simply memorizing the data. Right? If you don't regularize, if you overfit, you lose the ability to generalize. And losing the ability to generalize means losing any learning whatsoever. Right? Because learning is the ability to generalize from samples. Are we together, guys? Huh? So I will review quickly what all we learned. We learned that one of the easiest ways you can regularize is just get more data. If you get more data, like you see in the green line, automatically you get regularization. So more data regularizes your system. You can get more data by just going to the business people and saying, hey, I need more data. Or if you can't, then you can start slicing, taking pieces, rotating, doing all sorts of augmentation techniques based on what is it you're dealing with, text, images, tabular data, right? So for example, if you have a lot of missing values and you threw away those rows initially, one good way would be to just go and impute values, interpolate, do something, find the values, predict the values, interpolate it, and whatever, impute some value. And now you can salvage those rows. You have added more data. You can also do some amount of interpolation. Like for example, SMOD does class imbalance. It does by interpolation. So some classes are very few. So it goes around those data points in the feature space where the classes which have very few instances are there, and just goes and interpolates more points there. It comes with its risk, of course, because interpolation assumes that it truly, the in-between region is what you think it is. It can be interpolated into, it may or may not be true. So well, anyway, those are methods of data interpolation, data augmentation. That is one. The second way we learned about, and we learned about this fact that you always assume that your data comes from the same generative force underneath it. right? And that you have taken one observation is independent of the other observation. This is important, right? They should not be autocorrelated or things like that. And leaving forecasting aside, they shouldn't be. And so you make fundamental assumptions of independent and identically distributed. IID, it's a very fancy term. You'll see it all over the textbook. All it means is that in common sense term, you get bits of data, observations you take, and you take it from the same generative force that producing the data. You don't just hop around to different things. Okay. That's that. So when you do that, and of course, one easy way of doing that is when you capture a lot of observation, just remember to shuffle it up. Right? So that is that. Now, what is a node? A node takes, first of all, computes. Remember, we talked about it using resistors. Lots of resistors. These are your weights, W1, W2, for input X1, X2. And then you produce out of this a current Z, and that goes through the distortion function, right? So a node is both that bag of resistors and your distortion function, or more formally you say that node is first the linear combination of the inputs with the bias term, and then, so that is all of it put together is a affine transformation, and then comes a distortion function or an activation function applied to that affine transformation, to that Z. You get that. So that's something to remember. Now, early stopping approach, it just says that after a little while, just go and check that, stop the training, just go check how well your model is performing against test data. And if you start seeing a divergence between test error and training error, pretty much you get a clue that it's time to stop. You stop there, right? So that's that. The next way we learned is the dropout. Dropout is a little bit like Cheshire Cat. It's disconcerting. Suddenly a cat appears and disappears, where here the cat are the nodes. And what you do is these nodes, they tend to show up and then they tend to disappear. A small fraction of the nodes, randomly they appear, disappear. What it does is, as far as the next layer is concerned, in a way, it's showing it a subspace of the data, right? So that has its own benefit. We have talked about it in the previous workshops, why taking random subspaces is a good deal. Then we talked about L1 and L2 regularization. That is the heaviest of them all. Oh, somewhere in there we talked about the batch size, mini batch size, and how it affects, right? Then L1, L2, I think, where did we talk about the mini batch size? Did I write it here somewhere? I hope I did.
Close to batch normalization.
I talked about the batch size here. Right? So the thing is, don't take very large batch sizes, otherwise you'll start having overfitting, because you do want your error surface to fluctuate, your loss function, the loss surface to keep fluctuating reasonably, otherwise you'll get trapped in local minimums. Next we come to L1 and L2. L1 and L2 basically says that you don't want the absolute minima of the loss surface. You want to have the constrained minima, means a minima that is within the bounds, where the weights are all within the bounds of a certain distance from the origin. In other words, none of the weights can exceed a certain size, right? Or a sum total size is fixed using a distance measure. In the weight space, you can go only that far from the origin in search of the weight. Right? Now, the question is how far? Far is defined by Euclidean or Manhattan distance, and that leads to L1, L2 norm. L1 is Manhattan, L2 is Euclidean, as we just saw here. Right? So that is that. So that leads to some bit of interesting geometry in the parameter space. When we project down the loss, the contour surfaces, we see that we end up with a circle of certain size, and the circle is a circle in quotes based on whether it's a diamond for L1 and it's a true circle for L2. So based on that, it will touch upon the constraints, the error surface, and when it touches upon the error surface, wherever it touches upon, certain geometric conditions will be true, namely the orthonormal vectors will be pointing in opposite directions. And a consequence of that is, so you will have a condition like this, true. That when you refactor, what does it mean in terms of your error and your constraint equation, like for example this, it begins to spill out the derivation of your ridge and lasso regression. So L1, L2 are also called lasso and ridge regression. But in in the deep learning community, you just call them L1, L2. Right? So what L1, L2 do is they prevent your weights from getting blown up. And that summarizes all the regularization techniques you will encounter. Well, maybe I missed some. If you guys encounter any, you can do that. Now we have 5 minutes. I would like to take the 5 minutes to show you a particular, or not show you, but point you to this, to certain visualizations of the loss surface. See, these loss surfaces are very high dimensional spaces. But if you project it down to 2 dimensions, how do you project it down to 2 dimensions? You take randomly, you take some weight and some other weight, and then you ignore the other all other weights, and you just compute the loss at that point with respect to those 2 weights. Right? So the loss would again be a y-axis, the sort of the y-axis in some sense. In this case, you end up with a situation like this. If I randomly pick a weight and another weight, and I look at the error surface, of course, I'm looking at a 2-dimensional surface, and you can visualize it. There are mathematical arguments to show that this preserves the information of the much higher dimension space, and the visualizations are not misleading. They're actually quite informative. I would like to show that a bit to you today. Let me bring that here. Let me see if I'm sharing the computer sound. Share computer sound. So if you go here in the workshop, you'll see that today for review, I have added a section here called, what is it called? Loss function and gradient descent. So guys, your homework at this moment for today, tomorrow is, you see there are 3 videos here. One, gradient descent, back propagation. There are 2 videos. Please go watch those videos. They are 10-15-minute videos, 10 minutes each, or something like that. Watch these 3 videos. Hang on, let me increase the font size. Guys, are we able to see this on my screen?
Yes, very nicely.
So they are all by a group of people who call themselves 3 Blue and 1 Brown. And they put in amazing amount of effort in visualization and in very clearly explaining the mathematical concepts. In many ways, just what Khan Academy is to, or what Salman Khan is to school children and to early college, 3 Blue, 1 Brown is to, it's a continuation to the next level, to a little bit more advanced topics. And they do a great job. Right? So look into this, and then there's an article that you can read, which is there in this loss and the blessings of dimensionality. Read this article, and there is a paper. So this will give you an idea, but I will just go through it and show you things that I'm talking about. This is your gradient descent. How do you come down to a minima? Now, this article is written in a very interesting way. It almost goes and starts by asking, what's the meaning of life, or something like that. Very nicely done, but in a bit idiosyncratic manner. It says all life is movement, and so forth. So you can get a sense of how it starts. So you can see here, guys, do you see as you can imagine, you don't see the minima, but you can see that big valley that is forming right here. And you can imagine there's a minima down in there. And this is another point I wanted to make. Do you notice that this place is filled with ridges? Right? If you look at this picture a little bit carefully, do you realize that there are local minimas, but not deep local minimas in which you can get trapped? Right? You have a lot of ridges here. lots of ridges. So next time you are hiking in these regional hills in Fremont and Dublin, etc., observe how often you meet ridges and ravines and so forth, and you'll realize that quite often you have that. Now, there are excellent visualizations. I would like to show you this visualization. So it is the same thing. Do you see, guys, it's looking into the absolute minima, and it is showing you it almost looks like the hills around a house, around the Bay Area, isn't it? If you look a little bit, but except for this deep, deep, deep valley where you want your gradient descent to take you.
Where you throw the sacrifice.
So, and this is how, you can see the descent happening to a deep minima. Now, one of the things that comes is, what if there are multiple deep minimas in your loss function? You know that the loss function in neural networks is not convex, obviously. You see a lot of local minimas, but what if there are lots of deep minimas? Now, I argued that actually higher dimensional spaces are much more infested with saddle points, but that doesn't preclude there being a few, not one, but a few deep, like local minimas, deep enough that it can trap you. That has been a question that has been puzzling people until a body of research came out recently, and it showed that, you know what, all those deep minimas, they're interconnected to each other in an interesting way. There is a sort of a trail from one to the other and so forth. And what you need is, you need to pick any one of those minimas because they will all give you essentially as good predictions. This is a fairly recent sort of observation the researchers have made in this space. And I don't think there's a lot of general awareness about it. So it also sets moot this whole worry that what if I get trapped in local minima? First, there are not that many deep local minimas. And even if there are, you do hit upon a few. You just have to get into one deep enough minima because that will be your effective model. It will work. So do watch the videos. If you go to this website, you will find a lot of, they have an entire website. These people who did it, they have an entire website. And those of you who are interested in the paper, here is this paper tentatively. I've marked it as the paper that we'll walk through on Sunday. So this will sort of deepen the conversations we have had on the loss surface. It's an archive paper. So usually it's a little hard to understand, but I'm hoping that after the discussions that we have had now, it won't be that hard to understand. Right? So read that article which is given in data science, and then the discussions we have had in the class, do that. And on Sunday, we'll take this as a reading, right? A review reading for that. And I've mentioned it in the email in this. So this is your reading for Sunday afternoon, the paper reading that we'll do this week. The hope is, guys, that as we move out with the fundamentals, hopefully, once and for all, you understand loss surfaces and the gradient descent, and hopefully, you got, if you have been with me for ML 100, 200, hopefully now you have finally, like, every aspect of regularization is clear, mostly clear. And if you're completely new to this terminology, you at least got some sense of it, of what regularization does. In simple terms, it prevents overfitting. You can take a somewhat complex model, a very complex model, and you can try to beat down the oscillations, dampen it down to a much better behaved model, right? That's the point of it. So we'll do that. So guys, with that, I will stop. We did not do back propagation. Let us keep it for next Monday. I will end with that, and I'll open it up to questions.